Alright guys, this is note card number 9, which is the derivative of a function. We're finally doing some calculus. And so we're going to talk about this equation in a little bit. But first, I actually want to start down at number 4 here. These two equations you should recognize from note card number 8. We kind of skimmed over them. But in class, we talked a lot about why we need to use limits of these equations to get the derivative or the slope at a single point. So in class we looked at an equation kind of like this, and there was a point here, and we'll call that the x value of this was a. So we had a, and then we had another point, which was at a plus h. And we used Desmos to basically move that green point closer and closer to the yellow point. So we moved it closer to the yellow point, and then again closer to the yellow point. And there was a time when we put the green point right on the yellow point. And the problem was that our slope equation became 0 over 0, and so we couldn't evaluate it. We couldn't figure out what the slope at that single point was. So as we tried to go from an average rate of change to an instantaneous rate of change, it didn't work because we had 0 over 0. But luckily, we've talked a lot about limits, and so we decided that we could apply the idea of a limit to this situation. And so instead of actually moving the green point all the way onto the yellow point, we used a limit there. And we went through the math. The math gets a little hairy, but we were able to figure out that the slope of the tangent line was, I think it was 1.75. So we were actually able to calculate the slope of the tangent line. Now, that was a lot of work to find the slope at a single point. Okay? And remember, these equations down here, these limits, are the derivative at a single point. Okay, and both of these equations work for that, to find out a single point. But we don't want to go through that long-winded math every time. And so instead of looking for these slopes at just point A, what we're going to do is I want you to compare this equation down here to the equation up here. And what you'll notice is that instead of a, this equation has x in it. And so this is going to end up being the equation that we use for the derivative. Is the limit as h approaches 0 of f of x plus h minus f of x over h. And this will give us not just the slope at one point, but at every point on the function. Okay, this will give us a slope at every point on the function. And so, without getting into too many of the details right now, we'll talk more about this equation in class, so you can ask questions about it. But let's go ahead and apply this equation right here to question number 1. And we'll see how it works. Again, we'll talk a lot more about why this works in class, but right now let's focus on how this works. Alright, so we've got our equation f of x equals negative 5x plus 4. And this is asking us to find f prime of x, which means that we're going to take the limit of f of x plus h minus f of x over h. And we're going to call this is called f prime of x. And that's what's called the derivative. So we're finding the derivative of this function. So the way that we do that is we say, well, if f of x is negative 5x plus 4, then f of x plus h is going to be negative 5 x plus h plus 4. And then we subtract f of x, so minus negative 5x plus 4 over h. And if I sort of tidy up what's on top, we get negative 5x minus 5h. So negative 5x minus 5h plus 4. And then if I distribute this negative sign, we get plus 5x minus 4. Plus 5x minus 4. So you'll notice this right away. The 4's go away, and the 5x goes away with the negative 5x. So all we're left with, after this huge cancellation, is just negative 5h over h. Now this is a limit, right? Remember, this is a limit as h approaches 0. So the limit as h approaches 0 of negative 5h over h. Well, we spent a lot of time doing that kind of stuff. We just cancel out the h's and then plug 0 in, but there's no h's to plug 0 in for, so the final answer is just negative 5. That is the derivative of f of x. So f prime of x equals negative 5. And what that means is that the slope of this function everywhere is negative 5. And that makes sense, right? You didn't need calculus to figure that out. This is just a line with a slope of negative 5. So there's nothing monumental about this result, except that we are now going to be able to take slopes not just of lines, but of other more complicated functions. And that will be a really big deal. Now, f prime of 2, what we do is we say f prime of x equals negative 5. So f prime of 2, we're going to plug a 2 in every time we see an x, except there isn't an x. So the answer is just negative 5. And again, what this means is that when x is 2, the slope of this function is negative 5. Again, you didn't need calculus to figure that out, but we're going to be able to apply this idea to much more complicated situations, and it's going to be really useful. So, moving on. 2, evaluate the limit as h approaches 0 of this whole thing. What I want you to notice here is our original function. Okay? So if you look at the structure of this, f of x lives behind the minus sign. Okay, here's our minus sign. This is f of x. And then this has a really similar structure. We have 6x squared, but instead of x squared we have x plus h squared. We have minus 2x, except here we have minus 2x plus h. And then the 7 doesn't have an x, so that's why we don't see an x plus h. So this is this function, right? Or this equation. And what this is asking us to do is find f prime of x if f of x was 6x squared minus 2x plus 7. So essentially what we're doing is we're finding the derivative of 6x squared minus 2x plus 7. Alright, let's do that. So we're going to have to expand this out, and the math will get a little bit hairy, but we'll see what happens here. We end up with 6, and then this is x squared plus 2xh plus h squared minus 2x minus 2h plus 7 minus 6x squared plus 2x minus 7. And if I just go ahead and distribute the 6 to the x squared and all of that, we end up with all of these terms on the top of the equation. And a lot of them are going to cancel out. The 6x squared cancels with the negative 6x squared. The negative 7 cancels with the 7. The negative 2x cancels with the positive 2x. I'll do that in another color. So all of these terms end up going away. Okay. And we are going to be left with, on the top, 12xh. Actually, I'll do it in order. We are left with 6h squared plus 12xh minus 2h. And that's all over h. So now we're finding the limit as h approaches 0 of 6h squared plus 12xh minus 2h all over h. And there's an h in all of these. So we're going to factor out an h. We've done this before when we were doing limits. We're left with 6h plus 12xh minus 2. Oops, and that h got factored out of the 12x. So it's really just 6h plus 12x minus 2 over h. And then, just like we've been doing with limits, that h gets canceled out. And we're left with 6h plus 12x minus 2. Now, when we plug 0 in for h, the 6h is going to go away. And so all we're going to be left with is 12x minus 2. 12x minus 2. And those of you that are in IB or have done derivatives before, you know that the derivative of that function is 12x minus 2. So this is why. This is, in calculus, we call it first principles. We're actually sort of looking at the definition of a derivative and taking the derivative the long way. And you guys are going to have to recognize this equation. You're going to have to recognize that what it's asking you to do is take the derivative of this function right here. Now, next note card will come up with some shortcuts for getting to this result, 12x minus 2. But hopefully it makes sense how we got to that result, 12x minus 2, and why limits are important in that. Alright, moving on to number 3. If f of x equals 2x squared plus 1, then the limit as x approaches 0 of f of x minus f of 0 over x squared is blank. This is really just a limits question. And so f of x is that. F of 0 is 1. And so we've got 2x squared plus 1 minus 1 over x squared, which simplifies to 2x squared over x squared, because these 1's go away. And the x squareds cancel out, and I'm just left with 2. So the answer is 2. Number 4, if f of x equals x cubed minus 2, which is equal to f prime of 4. Now, f prime of 4, what this means is the instantaneous rate of change at x equals 4. So it's the derivative at x equals 4. Now, that's a derivative at a point. So we're really not looking for this equation. What we want to look for is, we want to look for the structure of this equation, or this equation. And what you're going to notice is there's an h in this one. A in this case is 4. Now we have 4 plus h. That's a plus h cubed, because this is cubed, and then minus 2. So that structure looks good. This is a plus h minus f of a. So f of a in this case would be, f of a would be a cubed minus 2, and that's, in this case, 4 cubed minus 2, which is what we see here. So this one is looking a lot like the structure a plus h, f of a plus h minus f of a over h, except that there's a 4 in for a. And that makes sense because we're looking for f prime of 4. This structure over here doesn't look like what we're looking for. It's a plus x cubed. And neither this doesn't have, well, this equation doesn't have an x in it. This equation doesn't have an a in the f of x part. So we shouldn't see a number in the f of x part based on this equation for the derivative at a point. So this second equation over here, it does not match the structure of the derivative at a point. So our only one that's equal to f prime of 4 is this first equation here, and that's because it matches the structure of the equation above. So our answer is just going to be equation number 1, limit number 1. And that is note card number